All right. Welcome back. Thank you very much. I know that we've had a lot of great conversations and a lot of great content happening here the past day and a half, and I want to thank you all again for being here. My name is Janelle Curtis. I am the Director of Development Programs at RoboNation, and it's my pleasure to introduce our plenary speaker for this afternoon. Mark Harris is with NVIDIA. I know many of you are familiar with this company. He'll talk a little bit more about the company itself and what he's doing. He is on GPU computing and is going to tell you a little bit about what he's doing on his end. I know a lot of you are familiar with some of the other products that they have, like JETSON. He's not on that side specifically, but would be happy to field some questions. And if we have a lot more questions, we can make sure to pass those along and get some answers for you. It is also my pleasure to announce that we are in conversation with them and are finalizing a partnership with them. So RoboNation and NVIDIA will be partnering on all of our RoboNation competitions for 2018. More details to come. We will be announcing that in one of our newsletters in the new year, probably January or February. So keep an eye out for that information. Thank you. And without further ado, Mark Harris.
Okay. Thanks, Janelle. I don't know how sensitive the microphones are. Thanks for having me. I'm going to talk to you today about GPU computing for AI and autonomy. And first, I just want to give a little bit of a backgrounder on NVIDIA, who we are, what we do. So at NVIDIA today, we definitely think of ourselves as an AI computing company, which is not where we started. We started out as a computer graphics hardware company, and we started building graphics processing units, or GPUs, and then on top of that, built a platform for general purpose computing known as CUDA. And in the last 5 years or so, that's been increasingly used for artificial intelligence, specifically deep learning, and more for robotics and autonomous machines. So I'll talk about quite a bit about AI. But I wanted to get started with GPU computing in general, because that's more my area. So what do we mean by GPU computing? Well, the idea is simple. You have an application, and it has some core routines that are very computationally intensive, but also very parallel. They have a lot of independent tasks, a lot of data to be processed. And so typically, a GPU-accelerated application takes those core routines and moves those to the GPU by parallelizing them, either using libraries or by writing custom code. And then the rest of the application, the sequential parts, continue to run on the CPU. So you have this heterogeneous system with CPUs and GPUs, and the application takes advantages of the strengths of each. So in 2006, well, backing up a little bit, before 2006, there were a number of researchers, including myself, who kind of recognized that GPUs were getting really powerful and that the shaders and the shading languages available for GPUs could be used for more than just graphics. And so there was quite a bit of academic research on applications of that. But you had to program it using graphics APIs and these shading languages, which were very graphics specific. And so it had kind of a very domain specific feel, and it was had a high learning curve. NVIDIA took notice of this and started and designed its first GPU designed for general purpose computing, which was launched in 2006 also, along with CUDA, which is a platform for parallel computing on GPUs. And the core of CUDA is a compiler called NVCC, which is a C++ compiler, and a set of extensions to C++ known as CUDA C++, which allow you to express parallel computations, compile and run them on GPUs. And so I apologize. I'm going to apologize to half the room. I'm sorry I put code in my presentation. The other half of the room, I'm sorry I didn't put more code in my presentation. This is it. So on the left, you have serial C++ code. This is just doing a vector addition. So you have two arrays, X and Y, and you want to do an element-wise addition of all of them. So on the right is the CUDA version of that, which is a parallel version. And it looks very similar, except that instead of a loop over all the n elements, we launch basically as many threads, as many GPU threads as we have elements. And inside the function, each thread computes an index I and then does one of those adds. So each thread is assigned an index by the hardware. It's actually a hierarchical index. We launch what we call a grid of threads that's divided into blocks. And so to launch that, to call that function down at the bottom, we call vecadd parallel, and we tell it how many blocks and how many threads are in each block. And so there I've got 4,096 blocks of 256 each, so I'm launching 1 million threads and doing 1 million adds. There aren't 1 million processors on the chip yet, but there are thousands of them. And so the hardware has resources to have many thread blocks and many threads resident on chip and then switch between them. So that's CUDA. But in addition to a language and a compiler, CUDA also includes a set of libraries and also supports an ecosystem of third-party libraries and tools and applications. On top of that, which really has fueled the growth in GPU computing. So if you are looking to accelerate an application, the first place you should look is at libraries, because often there's a drop-in solution to something you're already doing, such as linear algebra or FFTs. We have a QFFT library, or graph algorithms or other parallel algorithms, and then more recently, deep learning. CUDNN is a library that is accelerates core computations in deep neural networks, and it's been integrated into most of the popular deep learning frameworks. TensorRT is a deep learning inference solution. I'll talk about inference a little bit later. DeepStream is a SDK for building video processing pipelines around deep learning models. So that's the CUDA platform in a nutshell. And by investing in this platform for parallel computing on GPUs, we've seen great growth in the adoption and also the discoveries that have been fueled by GPU computing in the last 11 years. I'll just mention a couple. We launched CUDA in 2006. In 2008, we saw the appearance of the first GPU-powered system on the top 500 list of the world's fastest supercomputers. And by a couple years after that, a GPU system was the #1 on that list. And that system, Oak Ridge Titan, is still in the top 10 on the list. Today, it has, I think, 18,000 Kepler-class NVIDIA GPUs. These systems have been used for a number of discoveries. One of the big areas for GPU computing is molecular dynamics. So GPU computing has been used for modeling building the first atomic model of the HIV capsid, which is useful for understanding how HIV behaves when it enters the cell and how it interacts with proteins and things like that. Similarly, how the H1N1 virus mutates. That's been studied with GPU-accelerated molecular dynamics. And the world's first 3D mapping of the human genome. So not just the sequencing, but looking at it in 3D to see how it's the topology and how it behaves. But perhaps one of the most important discoveries that's been enabled by GPU computing is deep learning. Which is a really becoming kind of a revolution in computing. And so in 2012, there was a team from the University of Toronto led by Alex Krizhevsky who created a neural network architecture called AlexNet, which they trained using GPUs. And with it, they were able to win a competition. You may be familiar with ImageNet, the Very Large Scale Image Recognition Challenge, which is an annual competition for recognizing images from a very large data set with thousands of classes. And they were able to win by a very large margin. And since then, all of the winners of the competition have been neural networks, deep neural networks trained using GPUs. In 2015, Google's network was able to exceed the human level of recognition in that competition, and since then, or on that data set anyway, and since then, teams have been leapfrogging each other and just improving the state of the art in image recognition. There's a couple of trends that have been behind this rise of GPU computing and of deep learning on GPUs. One of those is the end of Moore's law and Dennard scaling, which is kind of the ability to shrink transistors while maintaining the same power density, which basically came to an end in about 2006. The result is that serial processor architectures aren't really keeping up with computational demands of the most expensive applications. And so researchers and developers have been increasingly moving towards more parallel architectures, so massively parallel architectures like GPUs and other similar technologies. The other trend is this trend in deep learning. It started with kind of what people call the Big Bang of AI, which came about because of three enabling factors. One of those is the improvement in neural network algorithms, so in the architectures of the neural networks and in the algorithms for training them, which greatly improve the accuracy achievable. Also, the availability of large data sets enabled by the internet and social media. There were now data sets large enough and with labels and classifications needed for supervised training. And then finally, the hardware capabilities required to train these complex models on large data sets in a reasonable amount of time. And GPUs were adopted for that starting about 5 years ago and increasingly so. So what we're seeing is deep learning sweeping across industries, used for everything from image and video recognition on the internet to speech recognition and translation. In medicine, it's being used for detecting cancer cells and other anomalies, and for predicting and even creating new pharmaceuticals. It's used for content-based search and captioning in media. It's used for face recognition and intrusion detection and malware detection in security and defense. And then, of course, autonomous machines. So NVIDIA is involved in self-driving car research, and we're developing products there. So we use neural networks for pedestrian detection, for lane tracking, to recognize traffic signs, and we've even trained a self-driving car end-to-end using deep learning. So basically, all the input is what the cameras see, and the output is the steering and acceleration, braking. So what I wanted to talk about a little bit is why are GPUs so good at deep learning? And so to understand that, well, I'm kind of a beginner at deep learning, and so I went and made these slides basically as an attempt to explain, why are GPUs good at deep learning. And so what is a deep neural network? Well, it's basically a neural network, which is a set of artificial neurons with weighted connections. And a deep neural network is a neural network with at least two what are called hidden layers, which are the intermediate layers between the input layer and the output layer. And what it computes at each artificial neuron is a weighted sum of the inputs to produce an output activation. So it's inspired by the human brain. It's not the same as the human brain, but it is inspired by it. And then in addition to that weighted sum and the nonlinear activation function that's applied to it, we need a learning algorithm, which can update those weights to reduce the error in the output, which might be a classification, or given a sequence, it might be a new sequence. So for example, for neural machine translation, things like that. And the learning algorithm uses gradient descent to update the weights in the direction of reducing the error. And so the algorithm that it uses to do that is called backpropagation, which is a way of computing the gradient of the function computed at each node with respect to the error, and then propagating that from the output back through the layers and updating the weights. So that's deep neural networks in a nutshell. But if you look at the core computation, if we're computing the outputs using a weighted sum on each of the connections between the inputs and the outputs, then it's basically it's a dot product for each of the outputs between the inputs and the weights. And if you have all those different nodes, then those dot products are basically stacked up and you get a large matrix multiplication. And those networks are growing. So, we have data sets with millions of samples. We have thousands of categories. And the network architectures are growing in complexity. So we have tens to 100s of layers. And this is a gross simplification because I'm not looking at the nonlinear activation function. I'm not looking at the bias. That's the bias term that's used. But really the core is matrix multiplication. And even in convolutional neural networks, you can cast that as matrix multiplication. And GPUs are really good at large matrix multiplication. This is an architecture diagram or a block diagram of the latest NVIDIA server GPU. This is the V100, the Tesla V100 GPU, and the architecture code name is Volta. The previous one was called Pascal. And before that was Maxwell and Kepler. So we tend to name them after physicists. You can see here that it's kind of a sea of these little blocks. And there's 5,120 of those, I think. But they're grouped in these streaming multiprocessors. So there are 80 of these streaming multiprocessors. This is one of them. And each one has 64 what we call CUDA cores. A CUDA core is basically an arithmetic logic unit. And there are 64 FP32 cores, 64 int32, and 32 FP64. That's double precision. But there's also a new core on Volta that we introduced this year, which we call the tensor core, because it's basically a special purpose matrix multiply and accumulate unit. So it operates on small chunks of the matrices. And by dividing up the matrix multiplies into these small chunks, we can apply the tensor cores to them and get very high performance. The tensor cores are designed for mixed precision computation. So they take in 16-bit floating point inputs and do a full precision multiply, or the output is full precision, 32-bit, and the accumulation is 32-bit floating point. So by optimizing the precision and the operations and specializing it to matrix multiply, we can get much higher power efficiency and throughput. And so Tesla V100 is capable of 125 what we call tensor teraflops, which are those mixed precision operations on matrix multiply and accumulate. But it's also capable of a raw 15.7 teraflops of 32-bit floating point. And it has 900 gigabytes per second of memory bandwidth. So it's kind of a computational beast. And that translates to improvement in matrix multiply and to deep learning. So this is showing a comparison of the Tesla V100 running on CUDA version 9, which came out this year, comparing it to the Tesla P100, which is Pascal, the previous architecture, running CUDA 8. So basically 1 year ago. And you can see that in single precision floating point GEM, which stands for General Purpose Matrix Multiply, which is part of the BLAS standard for linear algebra, it's up to 1.8x faster. So that's a good speed up. And if you look at mixed precision, so if your problem can tolerate 16-bit precision inputs, which a number of deep learning applications can, you can get much bigger speedups. In fact, over 9x measured on QBLAS mixed precision matrix multiply. Okay, so the result of building CUDA and the ecosystem that grew up around it and that we've nurtured and supported is that we have an entire platform with a number of technologies that can run CUDA applications and deep learning, which has led to NVIDIA becoming the world's leading AI platform. And so across a number of technologies, we have discrete add-in boards, so graphics cards. The Titan X is one based on Pascal. We just announced last week or 2 weeks ago the Titan V, which is a Titan GPU based on Volta. So these are kind of the high end. They're more targeted at AI training and research rather than towards games, but they're still the same form factor as a game card you might put in your PC. Next to that is what's called the SXM2. This is a server board. So that's the Tesla V100 there. It's passively cooled. You would just have a heat sink on it, and you put them in a rack mount server and blow air across them. And then we have full integrated deep learning systems called DGX. So the one on the left is the DGX Station, which is a desk-side system, a workstation with 4 Tesla V100s, a whole bunch of memory and CPUs, and NVIDIA's custom GPU interconnect called NVLink. And then the one on the right is the DGX1, which is a 4U rack mount server with 8 Tesla V100s. So it has a lot of computational throughput. A lot of organizations and companies are using those for training deep learning, deep neural networks, and saving a lot of time on that training. On the second to the right is our Drive platform, Drive PX2, which is for autonomous cars, autonomous vehicles. And it has 2 discrete CPUs, so desktop class GPUs, and 2 Tegra systems on a chip, which have CPUs, ARM CPUs and GPUs. So it's also very powerful, but it's designed for the automotive industry. And then finally on the right is JETSON, which is an embedded AI supercomputer on a module about the size of a credit card, a little bigger. And it has the Tegra system on a chip on it. I'll tell you more about JETSON in a minute. So it's pretty well known now that NVIDIA is the leader for deep learning training. But a lot of people don't know that NVIDIA GPUs are also really good for deep learning inference. So what's inference? Well, there's 2 phases for deep learning or for machine learning in general. You have training, where you train a model using a large data set to recognize or to translate or whatever the task is based on that data set. And then you need to deploy that trained model and use it to recognize new data or to translate new data that it hasn't seen before. And so that's known as inference. So one way to think about it is that training uses the backpropagation algorithm that I talked about to update the weights, and then those weights are fixed and saved, and you can deploy them, and then only forward propagation is needed for the inference computation. But inference, we think of inference as the next great challenge for deep learning because of a few factors. And the factors that make inference difficult are these. One is that the types and the variety of networks has exploded. So there has been just rapid and a high volume of work on improving the accuracy of networks for different tasks. And so convolutional neural networks are commonly used for image classification and recognition and segmentation, things like that. Recurrent neural networks have a time element and sometimes a memory or attention mechanism, and those are used often for sequences like natural language processing. Generative adversarial networks, or GANs. The idea here is you have two networks. One is you can think of it as a forger. It's trying to generate new data that could be recognized as from the training data set. And then the other is the arbiter or detector, which is trying to detect whether or not the produced data is from the training data set or not, so whether it's a forgery or not. And by training these iteratively, both of them get much more accurate, and you can use it to generate samples that are more and more accurate. And so I think one of the most famous examples of this is training it on this data set called Celeb A, which is celebrity photographs from from the red carpet. And they just get better at generating pictures of imaginary celebrities. But there are also, real-world practical applications, such as generating new molecules that might be useful as pharmaceuticals or things like that. And then reinforcement learning is where are networks that are used to train agents to perform tasks. So this is potentially very germane to the field of robotics and autonomous vehicles. The second factor that makes inference difficult is the explosion of the complexity of the network. So if you just look at image recognition networks, for example, comparing an example network, Inception version 4, which was released in 2016, to AlexNet, which was released 3.5 years before that, it's a 350x increase in the amount of operations and bandwidth required to train it. So these networks are getting more difficult to process very quickly. And then finally is the explosion in applications. So the explosion of different types of intelligent machines that we want to enhance with intelligence. So manufacturing robots, personal assistant robots, automated agriculture is another area. All of the many applications of drones and other types of autonomous vehicles, and robot-assisted surgery. Basically, you name a field, there's probably an application for autonomy, right? You guys are the experts in that. But the problem has been that, we need platforms that are powerful enough in terms of computational throughput and flexible enough so that we can run a variety of different types of applications on them, and power efficient enough so that you can use them at the edge. So in these autonomous applications, often you are untethered, or you run on batteries and things like that. So, and you don't have necessarily access to the cloud for computation. So you need an efficient and powerful and deployable platform. And so that's why we built JETSON, and it's in its third generation now, the JETSON TX2. And this is basically an AI supercomputer on a module. It's got more performance for AI, or for deep learning specifically, than 2 Core i7 PCs, and it runs in less than 10 watts. It has 256 CUDA cores. That's Pascal architecture, so the previous generation to the Volta, and it's capable of more than a teraflop of computation. And it runs Linux for Tegra specifically, which is a Linux modified to run on the Tegra system on a chip, which is the processor that NVIDIA makes. That's the core of JETSON. It runs the robot operating system, CUDA, all the CUDA libraries. Again, just like with CUDA, there's an ecosystem starting to build around this that enables you to build applications. So there's an SDK for JETSON called JETPACK, and it includes CUDA and Linux for Tegra, It can run a robot operating system. There's a number of libraries and SDKs that are compatible, including NVIDIA's deep learning libraries, OpenCV, VisionWorks, which is from NVIDIA, graphics APIs, so you can do rendering on JETSON. It has GPUs, so you can render. And it has video libraries and has onboard video encoding and decoding acceleration also. And then there's samples for it and our Insight developer tools, which is debugging and profiling. So basically you have everything you need to develop applications. So we're excited to announce the details are still being worked out, but NVIDIA is going to be sponsoring, as Janelle mentioned, RoboNation in 2018. And as part of that, we will have opportunities for you to get access to JETSON as well as desktop GPUs. But for now, we have an EDU discount, an academic discount, which would be available also to all the participants here for the JETSON TX2 developer kit, which is normally $599 retail. It's available for $299. That's US dollars. It may vary. Other countries, I don't know the details. But actually, I should mention, the previous slide showed the little gold JETSON card. That's the actual JETSON board, which if you were going to deploy, you might use that. But there's also, this is the developer kit. So it's a full board with active cooling and all the ports you need. It's got HDMI and USB and Wi-Fi and Ethernet, GPIO, and I think even PCI Express. So you can basically build whatever you need for development on JETSON. It's pretty cool, pretty fun little product. Okay, so when I got here, I wasn't aware before, but there was a lot of discussion about simulation. And so I quickly went and asked for some slides to add to my talk to cover a new project that we have called Project Isaac, which is an AI robot simulator. I guess one way that I think about this is kind of VR for robots, but in the talks today, there was a lot of discussion about the importance and the many ways that simulation can be really useful in these robotics competitions and in robotics in general. And NVIDIA recognizes that, and we have a number of technologies that we can apply to help this. And so we've started this Project Isaac, which is basically a simulation and training environment for AI for robotics. And when I say we have a number of technologies that we can apply, on the game side, we do very high fidelity graphics and rendering, and there are graphics libraries and engines available for that, as you probably know. But Isaac is based on a modified version of Unreal Engine 4 that incorporates all of NVIDIA's GameWorks technologies, which includes a physics engine that we call PhysX, which does physics simulation, a lot of it done on the GPU, so rigid body simulation, cloth simulation, fluid simulation, all these kinds of things. And so that you can incorporate that into your environment. And then, of course, you can interface that with deep learning frameworks and reinforcement learning, such as the OpenAI Gym and things like that. And then hopefully build environments to train your autonomous systems in, and then eventually deploy that. Now, I say build your environments, but I actually asked how you get a hold of this, and it's a little bit early for that. It's still kind of in the R&D phase. We're working with a few specific labs. But they've done a couple of cool demos, and I have a video to show you of Isaac. So let's see. So let's go full screen of that. And, oh, sorry, I need to rewind. Oh, you can't see it because I'm full screen on a different screen. I'll go back. If I can. Let me just reopen that. there we go. Okay, that's a different one. I'll show this golf one first. Now, where'd it go? I know how to find it. Okay. So if I go full screen, can you see it? Yes. Awesome. Okay. So this is using reinforcement learning to train this simulated robot called Isaac and to play golf. And of course, at first, he only has minimal knowledge of how to do it, right? He has an arm, he can swing a club, but you can see he swings it in kind of awkward ways. He can perceive the terrain, which is not flat. You know, it has curves. And you can see he's kind of there. He just sat there for a while. And then he gets scored, right? So if he gets it near the hole, he gets a higher score than if it goes far from the hole. If it goes in the hole, he gets more reinforcement. So he starts out pretty bad, and he gets better. See, he's getting close. Until eventually he gets quite good at it. Still missing at this point. Oh. That's a pretty good shot. I don't think this video has the one that our CEO showed. Oh, maybe this is it. Up the hill and back again. So, so he looks like a pro. So yeah, so that's Isaac. And you know, because you have this ability to use the graphics the engine and the physics engine, then you know the limits of the types of environment that you can build are well, the types of environments you can build are theoretically unlimited. I have one more video. I think am I all right on time? Yeah. Okay. Where'd it go? So this is kind of a cool video because this is adding in yet another technology that NVIDIA is heavily involved in, which is virtual reality. And so in this case, we actually have a human in the loop. So here they've trained Isaac to play dominoes. It's a fairly simple game in terms of the game. It's not, it's not Go, which, GPU trained deep learning has also won. But there's physics involved here because he has to manipulate objects, and so he has to perceive the world, see what you played, and choose a move and make the move in virtual reality. So, and he has to be cute also. So this is the human who's wearing an Oculus or something and playing the game with Isaac. So here, we use the physics engine to simulate the rigid bodies, and of course we're doing realistic rendering and right. So they're also using image recognition. I don't know the specifics of that. So they're the robot has to see the dominoes and then run a CNN on that and decide how to make a move. Oh, he doesn't have a move, so he passes. I guess that's the end. So the humans still win. It's not Skynet yet. Okay, so that's most of my talk. I just wanted to leave you with there we go, with a couple of resources to get you started, especially for teams that might choose to use NVIDIA platforms in the upcoming competitions. We have a number of resources to help you get started. There's what we call the Deep Learning Institute, which is nvidia.com/DLI. This has a increasingly rich variety of training and hands-on labs and online labs and even nanodegrees that you can do in deep learning, and I think there's even some lower level GPU computing training, CUDA stuff. And then 2 days to a demo is JETSON focus. So this is basically step-by-step guide to get you going on JETSON and build some kind of autonomous demo. I don't know what the specific demo is, but it's a good getting started. And then a little bit less applicable, if you're an AI startup, we have a program with marketing and free hardware and mentoring and things called Inception that's targeted at AI startups. And then last but definitely not least is the GPU Technology Conference, or GTC, which is NVIDIA's event for GPU developers. It's now multiple events worldwide. We do a kind of a flagship annual one in San Jose, and then later in the year there's events in Europe and Asia and East Coast of US and things like that. So that's my talk. I hope you found it interesting, and if you have any questions, I'm happy to attempt to answer them. Thank you.